In problem number 1, we're told we have a normal distribution with mean 50. If we consider the interval from 50 to 58, we are told that the proportion of the distribution within this interval is about 0.4452. We are asked to consider the interval for x less than 58. That is, if we consider everything below 58, that would include the additional left half of the bell, an additional 50% of the distribution. Thus, the probability that x is less than 58 is the sum of that left half of the bell in addition to the 44.5% we're given for the interval between 50 and 58 for a total of 0.9452. This simply uses the symmetry of the bell-shaped distribution. No calculator is necessary. The probability that x is greater than 58 is just the remaining portion of the distribution. That is, it's the complement. So 1 minus the 0.9452 that lies to the left gives a value of about 0.0548, just under 5.5%. Next, we're asked to determine the probability, or the proportion of the distribution, that lies between x equals 42 and x equals 58. Note that this is an interval symmetric about the center of 50. It extends 8 units to the right of center, as well as x units to the left of center. Thus, the area is symmetric about the center, which gives another 44.5% to the left. The two intervals are symmetric either side of center, which means the two areas are symmetric either side of center. Thus we have 0.4452 plus another 0.4452. That's a total of 0.8904, or about 89%. Finally, we're asked for the portion of the distribution that is less than 50. But checking our picture, we note that 50 is the center of the distribution. So the entire left half of the bell, or 50% of the bell, lies to the left of the mean of 50. This simply uses the fact that the total area under the curve is equal to 1, and based on the symmetry of the distribution, exactly half, or 50% of the bell, lies either side of center. That concludes problem number 1. In problem 2, we're told the distribution is normal, centered at a mean value of 30, with a standard deviation of 8. We're asked to consider the interval from 30 to 42, and find the corresponding probability, or portion of the distribution, for this interval. The probability that x lies between 30 and 42 can be computed using our normal CDF command. As we've seen before, by entering the interval, the endpoints 30 to 42, in addition to the mean and standard deviation, computing this value in our calculator gives a resulting proportion of about 0.4332. That is, the area under the curve, where the proportion of the distribution is just over 43%. In part B, we're asked to consider the interval from 18 up to 42. Note that a value of 18 is 12 units below the mean. That also corresponds to the 12 units above the mean. That gets us to the endpoint of 42. That is, this interval is symmetric, 12 units either side of the center. But by the symmetry of the distribution, that means another 43.32% of the distribution lies within this interval. That is, the total probability for these two intervals gives us 4332 twice, a total of 0.8 0.8664. In part C, we're asked to consider the probability x is less than 42. But since we've already determined that the probability between 30 and 42 accounts for 43% of the distribution, if we now consider all of the distribution for x values below 42, that interval extends all the way to negative infinity and includes the entire left half of the bell. Thus, together with the 43.32% that lies between 30 and 42, we have a total area, or a total proportion, of 50% plus 43%, or about 93.32%. If we instead consider the portion of the distribution that lies to the right of 42, well, that's just the complement. In other words, we can find that remaining area by subtracting from 1 our previous answer. The resulting proportion is the remaining 6.68%. Here we've taken advantage of the symmetry of the distribution to make the calculations easy, but any of these values could have also been computed using the normal CDF command. For example, on part D, if we consider the interval from 42 and beyond, that's 42 to infinity, for our bell-shaped distribution centered at 30 with a standard deviation of 8, would yield a result of 0.0668, which agrees with our earlier result. Thus, whether we take advantage of the symmetry of the distribution, or perhaps use the complement, as we did in part D, the answers are the same. In problem 3, we're told the average height of the hay crop is 38 inches, with a standard deviation of 1.7 inches. If we're asked to determine what proportion of the crop is greater than 40 inches in height, we're simply looking at that portion of the distribution that lies at a height of 40 or greater. That area under the curve, corresponding to this interval, is the proportion we're looking for. And as we've seen, that proportion, or area under the normal curve, can be computed using our normal CDF command, where here the interval extends from 40 to infinity, where the mean and the standard deviation are given. Making this calculation on our calculator, we find a proportion of just under 12%. That is, just under 12% of the crop is expected to measure 40 inches or more. In problem 4, we're given a normal distribution with mean of 86 and standard deviation of 5. We're asked to determine the 70th percentile. That is, we're asked to determine the cutoff, or location, such that the interval below that point contains the lower 70% of the distribution. We've seen before that such a location can be computed nicely using the inverse normal command, where the 70% is the area to the left of the location, and the mean and standard deviation were given. Computing this value on our calculator, we find the value of x is about 88.62. Thus, our location, that is described as the 70th percentile, is at 88.62. In problem 5, we consider a distribution of exam scores with mean 76 and standard deviation 8. We're asked to determine the score that would determine the top 15% of the distribution. That is, we're asked to determine the score that would cut off the leftmost 85% of the distribution. Thus, to find such a value, we can use our inverse normal command, where the area to the left of x is the 85% we enter into the calculator, along with the mean and the standard deviation for this distribution. Making the calculation, we find the score is approximately 84.29. Thus, a score of about 84.3 or higher would put your score among the top 15% of this class. For the distribution of house prices described in Problem 6, the average of $180,000, along with the standard deviation of $25,000, describes the distribution. We're asked to determine the interval of house prices that would determine the middle 90% of this distribution. We've seen before that if we have accounted for the middle 90% of the distribution, that leaves the other 10% of the distribution divided evenly among the two tails. Thus we have 5% in the left tail as well as 5% in the right tail of this distribution. To determine the corresponding values of x, or the home prices, for the two ends of this interval, we can use our inverse normal command because we know the area to the left. For the leftmost endpoint, the area to the left is just 5%. So entering this into our calculator along with the given mean and standard deviation allows us to compute this house price. Making this calculation, we find the left endpoint is about $138,878. We similarly compute the value for this endpoint using our inverse normal command, this time with an area to the left of 95%, along with the given mean and standard deviation. Making this calculation, we find a value of $221,121. Thus, the interval containing the middle 90% of our distribution of house prices stretches from $138,878 to about $221,121. Recall that any normal random variable may be converted to a standard normal random variable, z, using our z-score formula, where z equals x minus the mean divided by the standard deviation. Here we're told x equals 67 corresponds to the 80th percentile of the given distribution. There is a corresponding z-score that also corresponds to the 80th percentile of the standard normal distribution. We can compute that location using our inverse normal command. For an area to the left of 80% in a distribution with mean 0 and standard deviation of 1, we compute this value and find that the value of z is about 0.84. This location, 0.8416, is the 80th percentile and corresponds to the similar 80th percentile of the other normal distribution. Thus, the formula allows us to relate this z-score to the corresponding value of x based on the z-score formula, where here the mean is 55, but the standard deviation is unknown. But this equation, with only the standard deviation as the unknown, may be rearranged to allow us to solve for the standard deviation. That is, if we cross-multiply the sigma to the left-hand side of the equation, 67 minus 55 is a total of 12, and dividing both sides by 0.8416 allows us to solve for the value of sigma. That is, the standard deviation is about 14.26. Because we knew the mean and standard deviation for a standard normal distribution, we were able to compute the value of the 80th percentile. And since we were given the 80th percentile for the other distribution, the z-score formula allowed us to relate those two values, and in the end allowed us to determine the standard deviation of this second distribution. Our approach to problem number 8 is the same as we saw in problem number 7. This time we're given the 25th percentile of a distribution centered at 24. There is a corresponding 25th percentile for the standard normal distribution. We can compute that value of z based on our inverse normal command. The location cutting off the leftmost 25% of the standard normal distribution, where we know the mean is 0 and the standard deviation is 1, gives a resulting z-score of negative 0.6745. This is the value of z that corresponds to the similar corresponding value of x in our other distribution. Both locations represent the 25th percentile of their respective distribution. These two locations are related based on our z-score formula, where z equals the quantity x minus mu divided by sigma. Here our value of z, negative 0.6745, is related to our value of x, based on a mean of 24 and a standard deviation yet to be determined. Cross-multiplying by sigma, we have negative 0.6745 times sigma equals 18 minus 24, or negative 6. Thus dividing on both sides by negative 0.6745 allows us to solve for the value of sigma. That is, sigma equals negative 6 divided by negative 0.6745 for a value of approximately 8.9. The standard deviation we were looking for, the standard deviation of this second distribution, is approximately 8.9. In this problem, we're told the standard deviation, but we don't know the value of the mean. Thus we have a normal distribution with center unknown, but we are told that the 90th percentile is equal to a value of 87. Thus 90% of the distribution lies to the left of x equals 87. If we consider the corresponding value in the standard normal distribution, that is, if we consider the 90th percentile, we can find the corresponding value of z. Using our inverse normal command, we specify an area to the left of 90%, along with the known mean and standard deviation of 0 and 1. Making this calculation on our calculator, we find this value of z is about 1.28. These two locations correspond to the 90th percentile of their respective distribution, and these corresponding values of z and x are related by our z-score formula. That is, the value of 1.28 is related to the value of x equals 87. By subtracting mu and dividing that quantity by our standard deviation of 7.5 yields an equation that allows us to solve for mu. Cross-multiplying by 7.5, we're left with just 87 minus mu on the right side of the equation. Subtracting the 87 from both sides of the equation, making the calculation on the left, we find that a value of negative 77.4 is equal to the value of negative mu on the right side of the equation. Thus, we find that mu is approximately 77.4. Our distribution is centered at 77.4. In problem number 1, we were told the proportion of the distribution which lies between 50 and x equals 58 was about 44.5%. Together with the additional 50% which lies in the left half of the bell, we'd have a total area of about 94.5%. This value of x corresponds to a similar value of z in the standard normal distribution, which also cuts off the lower 94.5% of that distribution. The value of z can be found using the inverse normal command. Based on an area to the left of 94.5% and our known mean and standard deviation of 0 and 1 for the standard normal. Computing this value, we find a z-score of about 1.6. Thus we know this value of 1.6 corresponds to our value of x equals 58 based on the z-score formula. Here, with the value of z equals 1.6 and x equals 58, along with the given mean of 50, but the unknown standard deviation of sigma, gives us an equation that allows us to rearrange and solve for sigma. That is, cross-multiplying the sigma to the left-hand side of the equation leaves a value of 58 minus 50, or 8, on the right. Dividing both sides of the equation by 1.6 allows us to compute the value of sigma, and we find sigma equals 5. That is, for our distribution from problem number 1, we now know the standard deviation was equal to 5. We can verify this is correct by using our normal CDF along with the interval from 50 to 58 in our problem 1 distribution, where now, with the mean and standard deviation of 50 and 5 respectively, we can compute the corresponding area under the curve and verify that, as given in problem number 1, the resulting proportion is about 44.5%. Thus, if we had determined the value of sigma, we could have computed all the answers in problem number 1 based on our normal CDF command. But it was really easier to just take advantage of the symmetry of the distribution. And that completes the worksheet.